Hi folks, Buckley here. Welcome to lecture number 15 for MEEG102. Today we'll be covering engineering fits. I'm working through a lot more problems than we did last lecture. So, a couple announcements. Online lab number 7 is going to be this week. It'll be covering advanced assembly and auxiliary views. After number 7, you only have one lab left, okay? And I promise it'll be a really interesting lab. We'll be dealing with some advanced features in SolidWorks. I think you'll also enjoy online lab number 7. Individual assignments, assignment 5 is due this week by 5 p.m. on the day of your lab, so that's either a Tuesday or a Thursday. And assignment number 6 is now open. It'll be due in 2 weeks, and that will be your last individual assignment. Design project, you should be working on milestone number 8 with your team. That's detailed engineering design. We're expecting a full drawing packet. So you should be working on that, and that is due next week during your lab time, okay, so Tuesday or Thursday. Live sessions with me are optional, and I'd love to see you. Those are Tuesday, Thursday, 10:30 to 11 a.m., and you can see Canvas for your Zoom link. Honor students, you should be working on your maker profile, so that's going to be due in a few weeks. All right, let's get going. First up is going to be our quizette, 5 questions in 10 minutes. It's a timed quiz on Canvas. You got to complete it by 12 noon today, which is Tuesday, April 21st. Okay, so make sure you get that done. It'll be on the basics of engineering fits. Okay, a few things for today's lecture. So we're going to, just a brief reminder of where we are here. We are designing and specifying engineering fits. And there are 3 kinds of fits: a slip fit, otherwise known as a running fit, in which the shaft slides freely through the hole; a press fit, in which the shaft and the hole have an interference, right, so they don't slide freely; and a transition fit, which is somewhere in between. You can call it a sticky slip fit or a loose press fit, but it's somewhere in between. If we're looking at the math behind how engineering fits work, we tend to abstract everything as a shaft or a hole, even if the objects that we're dealing with aren't circular. Okay, we'll abstract them that way. So a slip fit, the diameter of the hole is greater than the diameter of the shaft, and you have yourself some space here. That's called a clearance. Okay, so d hole minus d shaft gives you a positive value called a clearance. For an interference fit, which you would achieve either by pressing the shaft into the hole with a lot of force, or we also talked about how you can use thermal expansion and contraction to work in your favor, either by heating up the hole to cause that to expand, or actually freezing the shaft, which would cause it to shrink. So interference fits, the diameter of the hole is less than the diameter of the shaft. So if you had d hole minus d shaft, you would actually get a negative clearance. Technically, we call that an interference. Okay, so we would typically represent this as a positive value of d shaft minus d hole. Okay, in between these two is our transition or location fits. The way these work from a fundamental sort of microscopic level is that the fit actually relies on irregularities in the geometry of the shaft or the hole, or surface irregularities, in order to achieve kind of a sticky slip fit. So the actual clearance is going to be very, very small. In some cases it may be negative, which is technically an interference, but the d hole and d shaft are almost equal to each other, and it could really go either way with which one is going to be slightly larger. So that's a transition or a location fit. All right, so we worked our way through an example problem where we were looking to fit a shaft and a hole together with a certain engineering fit. This is how that would be represented. Okay, so on your engineering drawings, if you want to achieve a specific fit, you typically don't just leave a call out for the machine shop. You actually want to specify what those values are going to be. I'm holding them to the 10,000ths of an inch. Okay, so that would be a very precision machining operation. Okay, so you could expect these 2 parts to be very expensive, but you basically have a min value and a max value. Okay, min and max for both of those. Okay, and notice that they're flipped. The order is flipped on the drawing. So max shaft is going with min hole, min shaft, or min hole is going with max or min shaft. Okay, so what do you need to prescribe one of these fits? Well, you need a little bit of information. First is you need to know which of these parts is going to be your stock. Okay, so that means which part are you actually buying off the shelf that has been precision made, and which part are you going to machine yourself or ask the machine shop to make. What's the nominal size? So the nominal size in this example here would be 3/4 of an inch, okay, 0.75, and that's the base dimension that you're working with to make all your calculations. Third thing is how tight or loose do you want your fit, which is called the fit class, and then those would be the 3 bits of information: basis, nominal size, and fit class. Those 3 bits of information we should see at the top of your any problem that you're working, that involves engineering fits. So we want you to specify what basis you were using, what is the nominal, and then what is the fit class that is requested, okay? All right, so how do you pick a basis and find a nominal size? So here's my little algorithm for you. If you purchased a stock shaft, okay, so if you went to McMaster-Carr and bought a stock shaft of a known dimension that's held very precisely to a certain tolerance, then you use the shaft basis. Otherwise, you're going to use the hole basis, okay? That includes instances where you are buying a piece that has a hole pre-cut, or instances where you are manufacturing both the shaft and the hole. You would use the hole basis by default, okay? So the basis determines how we set our maximum material condition. So if you remember, we talked about MMC, maximum material condition. When does the object in question have the most material? The MMC for the shaft is when you have your max shaft diameter, right? The biggest shaft is going to be the maximum material condition. That would be the instance where you set that to be the nominal value. So back in our previous example, if 0.75 was nominal, I would set my maximum shaft diameter to be equal to 0.75. Okay, if you're using the hole basis, the minimum hole is actually the maximum material condition, right? So that is when you have your most material on your part that includes that hole. So you would set 0.75 in that instance, the nominal value, to be equal to the minimum hole diameter. Okay, next bit is our engineering fit classes. So we have 3 basic fit classes, right? And they go by different names. So the first is a slip fit, otherwise known as a clearance fit, a running fit, or a sliding fit. Again, the hole in those instances, hole diameter is greater than the shaft. The ANSI designation is RC in that instance, and ISO, which is your metric, that's what the designation is shown there, right? H11, C11. Okay. For a force fit or an interference fit, otherwise known as interference, force, and shrink, are used interchangeably. Okay, the hole diameter is less than the shaft diameter. The ANSI designation is FN. Okay, and you'll see ISO designations for press fit, driving fit, or force fit in those instances. Okay, the middle condition, the transition fit, is called location, transition, or locational interference fit. The hole can be greater than or less than the shaft. Okay, that's going to be a very small value regardless. It has 3 ANSI designations, LC, LT, or LN, and the ISO designation is shown there, H7J6. Okay, so that's what we're looking at. All right, so last time we completed an example using the hole basis. So we had hole basis on this part, so this part would have been our stock, and we were going to manufacture the shaft. It was a 3/4 inch diameter nominal, and then we wanted a class RC3 fit. So we worked through that problem together. I encourage you to go back and rework that, okay, if this is all fuzzy to you right now. We're going to rework this problem and changing only one thing. We're going to change from using the hole basis system to the shaft basis system. And the situation in which this would be relevant is sort of as shown. I would expect for this type of part, actually what you would do is you would purchase the shaft and you would make this housing block for the shaft, okay? So if you purchase the shaft, you're actually going to be using shaft basis. So we're going to rework this problem in the shaft basis system. Okay, so I'm going to flip over to the document camera and we'll work this problem together. Okay, so what I'm looking at here is a shaft basis system, 3/4 inch nominal, RC3 fit. And I'm just going to remind myself with that I'm anticipating a clearance. Okay. So things that we're going to be looking for on your problem here, we really want to make sure that you have understood correctly the basis system that's being used. Okay, so they're check, and the nominal value and the fit class. So I should see those as stated at the top of any problem that you're working for me. Okay, if I now go to my table, let's pull my table up. Okay, and I'm going to copy these values because on the document camera they are a little small. But what I'm looking for here is I have a 3/4 inch RC3, which would put me right here. So RC3, 3/4 inch, right? So I have plus 0.8, minus 0.8, 0, minus 1.3. I'm going to write those down. Okay, those are values that I just took straight from the table. Plus 0.8, okay, 0, minus 0.8, minus 1.3. Now what do these things mean, right? So this is the maximum hole, minimum shaft, maximum shaft, right? So, or I'm sorry, minimum shaft, maximum shaft. All right, so these are values that you're going to add to the nominal value. They're stated in thousandths of an inch. That's important to remember, right? So this is 0.8 thousandths of an inch or 8 ten-thousandths of an inch that you're going to add to achieve the maximum hole diameter, right? And you're going to subtract 0.8 thousandths of an inch to get you the maximum shaft diameter in that instance. Okay, I can tell from this table, the way it's laid out, that this guy here is my MMC, right? My maximum material condition, because I'm not changing it from the nominal value. So my MMC 0 is equal to the minimum hole, which means that this is in the hole basis system. So the first thing I need to do here is I need to convert this table from hole basis. So I'm going to write this on here. This is in hole basis. I have to convert it to shaft basis. And that's just going to involve changing the 0 point on this table. Okay, so I want to reset this table such that my maximum shaft, right, which is my maximum material condition for the shaft, is equal to 0. So what I'm going to do is I'm going to start up here and I'm going to say negative 0.08 plus 0.8 is equal to 0. There, I've shifted that, right? But now I need to add 0.8 to every other cell in this table to keep the relative relationship between the parts the same, right? So I'm going to take negative 1.3 plus 0.8. That's going to be negative 0.5 plus 0.8 plus 0.8 is plus 1.6. And then down here I'm going to have 0 plus 0.8 is plus 0.8. Okay, so the values I've got are 0, negative 0.5, plus 1.6, and plus 0.8. Now I can use my table. Okay, so I'm going to use this table exactly the same way I used this one in the prior example, and just simply add these values to my hole and shaft diameters. So let me start with the hole. Okay, the max and the min. The maximum hole is going to be equal to the nominal, which is 0.7500 plus 0.0016 is 0.7516. The minimum is going to be 0.7500 plus 0.008 is equal to 0.7508. The shaft (0.7500) plus 0 for the maximum, right, because that's nominal, 0.7500. And down here, 0.7500 minus 0.000005. should be another 0 up there. 0, 0, 0. Okay, watch your zeros. 0, 0, 0, 5 is equal to 0.7495. Okay, now it's a good idea, just like we did last time, to check your clearance. Okay, so back on this table, there was a column right here that were your clearance values. Okay, this is a nice way to check whether or not you're actually doing all your calculations correctly, is if you get the same clearance. Okay, so even though I didn't ask for clearance in this problem, I'm going to go ahead and check it. So what is the clearance? This is a running fit, so I should have a positive value for clearance when I subtract the minimum hole from the hole diameter from the shaft the shaft diameter from the hole diameter. So let me start with the maximum clearance. Maximum clearance is going to be equal to the maximum hole diameter, 0.7516, minus the minimum shaft diameter, 0.7495. That's going to get me 0.0021. Okay, minimum, I'm going to have the smallest hole, which is 0.7508, minus the biggest shaft, which is 0.7500, is going to give me 0.0008, or 8.8 thousandths. Okay, if I go ahead and check these values on my table, I'm going to see something that says plus 2.1, plus 0.8 for my clearance. And again, the table is showing these in thousandths. Okay, so these match up, and I have the correct answer there for my clearance. So I know that my values up here, what we tend to be looking for, right, is what we need to prescribe to the machinist, which are those values for maximum minimum hole and maximum minimum shaft. All right, so now we know how to work in both the hole basis and the shaft basis system. What we're going to do for the remainder of today's class is we're going to practice. We're going to work through a bunch of practice problems together. Okay. So you have this packet. I released this on Canvas. And we're going to work through these one by one. Okay. So let's start with this question 1. Assume a half-inch shaft is to spin freely where accuracy is not essential, but where there's still a lot of contact force between the shaft and the hole. Okay, so that's explaining why you chose a particular fit that you chose. Therefore, an ANSI RC7 fit class has been chosen. Use the hole basis system to determine maximum and minimum allowable sizes of the shaft and holes, as well as max-min clearances. So I want both the sizes and the clearances. Okay, so let's go through and we write everything that we know about this problem. So we have half-inch nominal, we have hole basis, and we have RC7 fit. Okay, good. All right, now it's time for me to use my table. So on the table, RC7 is going to be a pretty loose type of a fit, right? Pretty big clearance there. Okay, so I'm going to come in and I'm going to look for half-inch RC7, and it gives me these values. Okay, and I'll go ahead and transfer them over so that we can see them. So my values for hole from the table and shaft from the table look like this. Plus 1.6, 0, negative 2.0, negative 3.0. All right. Since I'm in the hole basis system, I can use the information directly from the table. So for the hole, I like to set my problems up this way just because it keeps things nice and neat. I can see my calculations, so I'd recommend it. Okay, maximum hole is going to be 0.5000 plus 0.0016, give me 0.5016. Okay, that's that value. Minimum is just going to be equal to the maximum material condition, okay? My minimum hole, again, being my MMC in the hole basis system. For the shaft, I have 0.5000 minus 0.0020 is going to give me 0.4980. For my minimum, I'm going to get 0.5000 minus 0.0030 is 0.4970. Okay, so these are my maximum and minimum allowable sizes. I would let you leave it in that form right there. That's totally fine. Okay, sometimes I'll ask you to enter it into a table. For the clearances, again, I should be able to check this with my table. My max clearance is going to be equal to my biggest size hole, 0.5016, minus my smallest size shaft, 0.4970. That's going to give me 0.0046. And my minimum clearance is equal to my smallest hole, 0.5000, minus my biggest shaft, 4980, is equal to 0.0020. Okay, so let me just go ahead and check that with my table. So if I pull my table back up again, I'll see 2.0 and 4.6, okay, 2 thousandths and 4.6 thousandths. Therefore, these values check out, which is great. Okay, so let's rework this problem. Now we're going to be asked in the second part to basically rework this in the shaft basis system. Repeat this analysis for an RC7 fit for a nominal half-inch size using the shaft basis system. Determine maximum minimum allowable sizes as well as the maximum clearances. Okay, so on this guy here, I'm going to just repeat what I got up there. Half-inch nominal, shaft basis, and RC7 fit. Okay, so first thing I need to do is I have to convert the hole basis to the shaft basis. So let me go ahead and do that. I'm going to fold this paper up just a little bit so we can all see. Okay, so my hole, to convert from, again, from hole basis to shaft basis, I want to take the shaft, the MMC for the shaft basis, which is going to be my maximum shaft, and I want to set this cell equal to 0. So I'm going to take minus 2.0 plus 2.0 equals 0, okay, which means that I have to do the same thing on every other cell. I have to add 2 thousandths. So plus 1.6 plus 2.0 equals plus 3.6. 0 plus 2.0 is equal to 2.0. So I have 0, minus 1, plus 3.6, and 2.0. From there, everything is the same, okay? So my hole max min, hole max is 0.5000 plus 0.0036 is, falling off the edge here, 0.5036. Min is going to be, minimum is going to be 0.5000 plus 0.0020 is 0.5020. For the shaft system, or for the shaft, max min, my max is just going to be equal to the nominal, 0.5000, and my minimum is going to be 0.5000 minus 0.0010 is equal to 0.4990. Okay, now if I did this right, I should get the same clearance values. Okay, same clearance values. So the clearance values are tied to the fit and to the nominal dimension, not to the basis system that you're using. So whether I'm shaft basis or hole basis, I should get the same clearance for an RC7 fit on a 1/2 inch nominal. So if I do this right, I should get the same values for clearances that I got up there, okay? So clearance, let's go with our, push this up a little bit. Our max value, again, is equal to the maximum hole, 0.305036, minus the minimum shaft, 0.4990, is going to give me 0.0046, 0.0046, check. And my minimum is going to give me the smallest hole, 0.5020, minus the largest shaft, 5000, gives me 2 thousandths, right? Which is what I'm getting up there too. Okay, so all this checks out. So there's an example of a classic problem, okay, where I am asking you to work out the maximum minimum hole diameters first in the hole basis system and then in the shaft basis system, okay? And everything should be consistent. You should be getting the same clearances for both of those. All right, let's work with another fit type, okay? So next up, we're going to say, assume a 3-inch shaft and hub are to be permanently press fit together for a drive system, okay? In this case, the fit class chosen is FN4. Use the hole basis system and determine maximum minimum allowable sizes as well as the interference. Okay, so permanently press fit together, okay? So I would expect in this instance, because it is an interference fit, that I would have a negative clearance or a positive interference value, and that my shaft would be bigger than my hole in those instances. Okay, so let me write down everything that I know about this problem. Right? So I'm using the hole basis. I've got a 3-inch nominal, and I want an FN4 fit class. Okay, so with that, I'm just going to go over and I am going to find my fit class. Sort through my papers there. Locational fits, force fits. There we go. Okay, so FN. So I've given you a whole bunch of tables here that you guys have. You'll have these on the exam as well. Okay, so an FN fit class, FN4 is going to be this column. 3 inches is going to be this row. So that gives me this cell here. Okay, so I'm going to write those values down because they were a little small. So what I'm seeing on that table is the following: plus 1.2, 0, because I'm in the hole basis, plus 4.7, plus 4.0. Okay, so my hole shaft, just setting myself up here. All right, my minimum hole, which is my maximum material condition, is going to be equal to 3.0000. My maximum hole is going to be equal to 3.0012, right? My maximum shaft is going to be equal to 3.0047, adding 47. And my minimum shaft is going to be equal to 3.0040. Okay, so just doing that math in my head. I'm okay with this, okay, so long as you get these numbers right. So the risk is on you if you don't want to write out that equation. Okay, but in this instance, I'm just adding 4 thousandths, 4.7 thousandths, 1.2, which I can read straight off the table. Okay, next thing it asked for was the maximum minimum interference. Okay, I should be able to check this from my table. Okay, so my table is going to display interference values as positives, right? So I need to make sure that I've got my definition of interference correctly. So interference has the opposite express, it's going to be the negative of clearance, right? So negative clearance is interference. So my max interference is going to be the biggest shaft minus the smallest hole. So the biggest shaft is 3.0047 and the smallest hole is 3.0000 is going to give me an interference of 4.7 thousandths of an inch. My minimum interference in this case is going to be equal to the smallest shaft, 3.0040, minus the biggest hole, right, 3.0012, is going to give me 0.0028 inches. Okay, so the shaft is bigger than the hole by a range of 2.8 thousandths to 4.7 thousandths. That's actually pretty big. You're probably going to use either a lot of force to drive those two parts together, or you're going to use some of that, the thermal expansion and contraction that we mentioned earlier. But let me go ahead and check these values. So if I pull my table over, okay, just like with the clearance values on the RC tables, for the FN tables, you're going to see interference values. That value is 2.8 and 4.7. 2.8, 4.7. Okay, so these two check out. Okay, so you just did your first problem with a press fit. Now let's do another guy here. Let's do a location. So we'll kind of work our way through all the fit types. Okay, so we'll do a location fit. This is interesting because we'll see how this turns out in terms of whether the hole is bigger than the shaft or the shaft is bigger than the hole and what those clearances are exactly. Okay, so you want to achieve an LC3 location fit on a 1.5 inch shaft. Okay, use the hole basis system to determine allowable sizes and calculate clearance. Okay, all right, so my known information is hole basis, 1.5 inch nominal, LC3 fit. Cool. Let me go ahead and get that table. LC fits. Okay, LC3 is going to be this column here. 1.5 is going to give me the cross in this row. So I'll go ahead and write down those values. Plus 1.6, 0, 0, minus 1.0. Okay, so setting myself up. So for maximum, I'm going to have 1.500 plus 0.0016 is 1.5016. Minimum is 1.5000. Max shaft. Notice this is an interesting table, right? Because you could interpret it as either being in the shaft basis system or the hole basis system. They're both zeros there. Okay, but this setup will always be in hole. This is just particularly how it wound out for this class of fit. Okay, so the shaft is going to be also 1.5000, the maximum shaft. Okay, and the minimum shaft is going to be 1.5000 minus 0.0010 is 1.4990. Okay, so the clearance, it's asking me for clearance, not interference, so make sure you're clear on that. The max is going to be equal to the maximum hole, 1.5016, minus the minimum shaft, which is 1.4990. That's going to give me 0.0026, 2.6 thousandths. My minimum clearance is going to be equal to my minimum hole, 1.5000, minus my maximum shaft, which is also 1.5000. So that is actually 0. Okay. All right, so let me see from my table what values I'm getting for my clearance. So these are listed as clearance. I have 0 to 2.6. 0, 2.6. Okay, so that checks out. All right. One more question here, folks. This one we're going to deal with metric. Okay, and metric is a little bit different. Assume a 30 millimeter nominal dimension, use the shaft basis system, and determine maximum and minimum allowable sizes for, this is your fit class. So 30 mm nominal, shaft basis, okay, blah, 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 blah. All right. So let's write down what we know. First off, I'm just going to put really big on here. It's metric. Second, I have a 30 mm nominal. I'm going to use the shaft basis. And my fit type is an H9, D9 free running. So this is going to be a slip. Okay, so I would expect a positive clearance there. Okay, now I want you guys to look at the metric table that I provided you. Okay, and there's a couple things that we want to really look at with this table. Okay, so the first is that the table itself actually gives you values, so you don't have to do any math necessarily. It actually gives you, for a 30 millimeter nominal, it's actually giving you what the values are for the maximum and minimum associated with that nominal. Okay, so you don't have to add or subtract thousandths of an inch, which is cool. But the trick is, these tables are going to come to you in the shaft basis system. Okay, so and there may be instances where they would have it in the hole basis, but the tables that I'm providing you, they're in the shaft basis system. So actually, I could read directly off of this, this table what my values are going to be for 30 millimeter nominal, D9, H9 free running. It gives me these values right here. And let me go ahead and blow those up. Okay, so what you're seeing there is hole, shaft, .117, 30.065, 30.000, 29.948. Okay, so you actually see the values themselves. So really, all I got to do is just copy straight from the table, and I would be fine if you don't even write that there. You just say copying from the table. Your maximum hole is 30.117. Minimum is 30.065. Maximum shaft is 30. And note that it's really important, we're using the shaft basis system, so the nominal value should be the max shaft in this instance. We're going to do this same problem in hole basis in just a sec. Okay, but I can copy straight from the table because I am in shaft basis. The table provided was shaft basis. Okay, so make sure that's clear in your head. Okay, and then the minimum is 29.48. Okay, so the tables are set up a little bit differently in metric. Okay, let me calculate my clearance though. And I would expect you to still calculate the clearance. Actually, the clearance values are also provided like in the other tables. Okay, but it's a good way to check. My max clearance is going to be equal to my maximum hole, 30.117, minus my minimum shaft, 29.948. Okay, is going to give me 0.169 millimeters. And minimum is going to be my minimum hole, 30.065, minus my maximum shaft, which is going to give me 0.065 millimeters. If I go back to my table, I'll see right here 0.169 and 0.065. Okay, so those values check out. All right, let me just explain how you would do this for the whole basis system. So let's use what we know about shifting from shaft, between shaft and whole basis to get to solve the same problem, but in the whole basis system. So again, it's going to be metric, just rewriting what I know, 30 mm nominal, whole basis, and it's an H9D9. Okay, the big thing here is I'm going to shift. So in whole basis, I basically want this guy here to be 0. My maximum material condition for the whole, which is my smallest whole, should be equal to the nominal. Okay, so I'm going to shift my base. So if I want this value, 30.065, to be equal to 30, I would subtract 0.065, and that's going to give me 30 as my nominal, right? So I would need to do that to every other cell. So I need to subtract 0.065, and that's going to give me 30.052. So 30.052, 30, 29.935, and here I'd have 29.948 minus 0.065. That's going to be equal to 29.883. Okay. So I'm resetting my nominal condition here. So I want this guy to be equal to 30 instead of up here in the shaft basis, my maximum material condition for the shaft, largest shaft size, was equal to the nominal. So I'm resetting my nominal. Okay, so just making this super clear. For the whole, my maximum is 30.052, minimum is 30 flat, which is my nominal, which is correct. For the shaft, I have 29.935, and for the minimum, 29.883. If I want to compute my clearances, which again should match with what I've got up there, for my max, I've got my biggest hole, 30.052, minus my smallest shaft, 29.883, should give me 0.169. That checks out. And for my minimum, I'm going to have my smallest hole, which is 30 flat, minus my biggest shaft, 29.935, is going to give me 0.065, which also checks out. Okay, so a little bit different setup on the metric tables, but otherwise the process is super similar. Okay guys, that's what I have for you, and well done practicing.